Simple harmonic motion. We have question number 3, October, November 2007. A spring is hung from a fixed point. A mass of 130 grams is hung from the free end of the spring, as shown in figure 3.1. We have a spring and we have the mass of 130 grams. The mass is pulled downwards from its equilibrium position through a small distance d and is released. The mass undergoes simple harmonic motion. Figure 3.2 showed the variation with displacement x from the equilibrium position of the kinetic energy of the mass. Okay, we have the graph and we have on the y-axis kinetic energy in milligrams. So we have millijoules. We have the kinetic energy on the y-axis in millijoules, and we have the displacement on the x-axis in centimeters. So we are going to go to the questions. Use figure 3.2. So we are going to depend on the graph to determine the distance d through which the mass was displaced initially. So we need to find the displacement or the maximum displacement. Maximum displacement, which is the amplitude. So we are going to check the maximum displacement. I'm going to magnify the picture a little bit, and we are going to look here. We have 0.5 and we have 1. Did the division 0, 0.5 and 1. So the division is 0.5 for one division. Let's count. We have 1, 2, 3, 4. We have 4 divisions with 5 small division each. So we are going to count 20 small divisions. So we have 0.5 over 20 small divisions. Let's calculate it. So I'm going to use my calculator. 0.5 divided by 20. It gives us 0.025. So we have 0.025. So this smallest division here we have, it's equal to 0.025 centimeters. And we have 2 here, so we are going to multiply it by 2. It will give us 0.05. So we have 0.05. And we have the half here, and the half of 0.5 is 0.25. So we are going to add 0.50 plus 0.25. It will give us 0.75. Okay, we have 0.75 plus 0.5 plus 0.05. It will give us 0.8 centimeters. So the maximum displacement is 0.8 centimeters. So we are going to write here 0.8 centimeters. 0.8 centimeters. So the displacement d through which the mass was displaced initially is 0.8 centimeters. Show that the frequency of oscillation of the mass is approximately 4 hertz. So we need to calculate the frequency. We have an equation, and this equation to determine the maximum kinetic energy. We have 2 positions. We have a position where kinetic energy is 0, and we have a position where kinetic energy is maximum. Kinetic energy is maximum at the equilibrium position. Where the displacement is 0, we have maximum kinetic energy, and here is the maximum kinetic energy. We need to calculate this point to find the maximum kinetic energy. At maximum kinetic energy, we have the maximum speed or maximum velocity. Let's count here. Also, we have 4 divisions, and the distance between them is 1. So 1 divided by 20, it will give us 0.05. So 1 divided by 20 is equal to 0.05, correct. And we have 2 divisions. So 2 divisions means we have 2.50 plus 1 division, which is 0.05. So it will give us 2.05 but it's not on that right exactly this line. So we need to check it's a little bit above it, so we can estimate it So I'm going to estimate this value into it will be 2.56 millijoules. So the maximum kinetic energy is 2.56 millijoules. So we are going to move down. Here we have the maximum kinetic energy. So I'm going to write maximum KE equal 0.56 millijoules by 10 to the power of negative 3 joules. And we know that maximum kinetic energy is equal to half m omega squared the amplitude, or x naught squared. Okay, so we need to find, is working for finding the frequency. So we are going to consider omega squared is unknown, and we are going to substitute with the mass. Do you remember the mass? We already calculated the mass, and the mass was 100, or it is given for us about, remember, it's 130 grams. So 130 grams, we are going to multiply it by 10 to the power of negative 3 to convert into kilograms. So 130 times 10 to the power of negative 3 kilograms. And we have the kinetic energy already. We already calculated from the graph, so we can find omega squared. So omega squared is equal to 2 times kinetic energy, maximum kinetic energy, over divided by m x naught squared, and of course we are going to find the root for omega. So omega is equal to square root the values. We have 2 times the kinetic energy is 0.56 times 10 to the power of negative 3, since we have millijoules, divided by the mass. What is the mass? We said 130 times 10 to the power of negative 3, multiplied by x, which is the displacement, 0.8 times 10 to the power of negative 2, all squared. And we are going to put this on the calculator. It will give us 24.8 rad per second. Omega is equal to 2 pi f, so we can find f is equal to omega over 2 pi. So omega is already 24.8 over 2 pi is equal to 3.95 approximately 4.0 hertz. So the frequency is 4.0 hertz, as the examiner asked us to find. So we found it, the frequency. 6 marks for this part. And then we are going to move to the other part. On figure 3.2, draw a line to represent the total energy of the oscillating mass. Since the total energy is constant, so we are going to find we are going to draw a horizontal line to the maximum kinetic energy, because we know that we have a simple harmonic motion. Any increase in the kinetic energy, and the other side we will have a decrease in the potential energy, but the sum of kinetic energy and potential energy always constant. So we are going to draw a horizontal line from the maximum kinetic energy, and we have borders, so we need to put marks here. So we are going to put marks here. I'm going to put the mark, and after this by 2. So here is the point on the left, and we have, or we can put it up, no problem. So here, and after it by 2 divisions, and on the left hand side we have here also, and after it by 2 divisions. So here is the borders or the limit. I'm going to bring the ruler, and I'm going to place the ruler here horizontally, and then I'm going to draw the line. The line will be from that point till the other point on the left. Okay, so now we can erase this marks here. So this line represents the total kinetic energy. We can mark it here, the total kinetic energy. And we are going to remove the ruler, and we are going to move back. Double I, after many oscillations, damping reduced the total kinetic energy of the mass to 1.0 millijoules. For the oscillations with reduced energy, state the frequency. We know that frequency stayed the same. Frequency won't affect it even the time period. Actually, it will be affected by very small amount, but we are going to ignore this small amount and we are going to consider the frequency constant. So the frequency stayed the same with the value 4.0 hertz. Using the graph or otherwise state the amplitude. We need to find the amplitude, so we are going to make a small calculations. We have the total kinetic energy and we are going to write the equation like this. We have the total kinetic energy. Total kinetic energy is equal to what? Is equal to, or maximum kinetic energy, sorry, equals half m omega squared x naught squared. So we'll find that half is constant, m is constant, and omega squared, since the frequency is constant, so angular frequency is also constant. So kinetic energy is proportional with the square root of amplitude. So if we are going to say kinetic energy 1 over kinetic energy 2 is equal to amplitude 1 squared over amplitude 2 squared. We are going to find the amplitude 2. If the total kinetic energy in the beginning was 2.56 times 10 to the power of negative 3 over kinetic energy in the second case 1.0 times 10 to the power of negative 3 is equal to amplitude. The first amplitude was 0.80 centimeter, 0.80 centimeter over 0.8 centimeter squared over amplitude 2 squared. We need to find amplitude 2. So I'm going to work to find amplitude 2. We are going to move down a little bit. So amplitude 2 is equal to square root, and we are going to substitute 1.0 times 10 power of negative 3 multiplied by 0.80 squared over 2.56 times 10 power of negative 3. We are going to cancel out this and we will have it. We can do it under the calculator. You will find that it's equal to 0.5 centimeter, 0.5 or 0.50 centimeter. So the amplitude would be at 0.50, so I'm going to return back 0.50 centimeter. And we finished this problem. See me in another problem.